All right, these are the exercises from the end of the handout, and the point of each of these is to say, for each of these tableaux, which candidate does the grammar predict is optimal? That is, what's the output or the winner in each of these tableaux? And these are done with abstract candidates that don't have any actual content and abstract constraints that also don't have any actual content. And the idea is beyond the general work of figuring out what constraints look like, and what kinds of things occur in different languages, there's also just some low-level sort of technical detail that you need to figure out how OT Tableau work. Now, in general, when you're doing problems for the homework and in this class more generally, we're not usually going to be taking fully filled in Tableau and trying to figure out which candidate is the winner. More often, we're going to be trying to figure out how to arrange the constraints in a particular way to get a particular winner. But in order to do that, you need to know these low-level details. So it's worth making sure that you understand how the OT evaluation algorithm works. All right. So in this first one, we have two candidates, number one and number two. We have two constraints, number one and number two. Constraint number one is ranked above constraint number two, and there's only one violation in the whole tableau. Candidate one violates constraint two once. So, which candidate wins? The answer is B, candidate two. This is the winner. Why is that? Well, because we start at the highest rank constraint. What's the minimal number of violations here? 0. Does any candidate violate it more than the minimal number of times? No. So we conclude nothing. Move on to the next constraint. What's the minimum number of violations here? 0. Does any candidate violate it more than the minimal number of times? Yes. We have one violation for candidate one, so we eliminate that one from consideration. The only remaining candidate is candidate two. Now, in a real OT tableau, if you end up with a candidate like candidate two here, that doesn't have any violations at all for any of the constraints, the odds are that something has probably gone wrong in your analysis. Most likely, you either forgot a relevant constraint that should have been in the tableau that candidate 2 violates, or maybe you miscalculated whether it violates one of these constraints. In general, we're usually not going to see Tableau where there's a candidate that just violates nothing in the language. There might be a few times when we limit our attention to certain constraints and we end up with this, but in general, it's going to be a pretty good sign that there might be something wrong with the Tableau. Okay, next one looks exactly the same, except we've now added an extra violation mark. And which one is the winner here? The answer is candidate 1, so A here. Why is that? Well, we start with the highest rank constraint. What's the minimum number of violations? 0. Does any candidate violate it more than the minimal number of times? Yes, candidate 2 does. Violates it once, therefore eliminate this candidate from consideration, and we're already done. We don't even need to look at constraint 2 in this tableau. And this is a property of OT. If there are higher rank constraints that fully determine the optimal output, then you don't even need to consider the lower ranked ones. Although if I'm asking you to put violation marks into a tableau, I want all of the violation marks, not only the ones that are relevant to the highest constraints. Okay, next one. Which candidate wins in this tableau? This one's a bit tricky, and that's because it's a situation where there's some constraint here that, at least with regard to the candidates we're considering, cannot be satisfied. And so what we end up with here is the highest rank constraint. What's the minimal number of violations? Well, in this tableau, it's 1. Does any candidate violate it more than the minimal number of times? No, they both violate it exactly once. Therefore, we don't discard any candidate at this step. We progress to constraint 2. Here, what's the minimum number of violations? Well, here, it's 0. Does any candidate violate it more than the minimum number? Yes, we have one violation for candidate 1. Therefore, candidate 2 is optimal. Right? So another way of putting this, if all the candidates tie on some higher rank constraint, then the optimal output will be decided by a lower ranked constraint, if there is one that can decide. Oh, I should also say, in formal terms, sometimes, probably not so much in this class, but sometimes when you have this situation where every candidate violates the constraint some number of times, you might see people just erase these marks. And what they're saying there is, well, no candidate violates it more than any other candidate. So we're just going to erase all the marks and count them all as zero. It doesn't make any difference. The winner is going to be the same in either case. Okay, next one. Uh, which candidate wins here? We have candidate 2, which violates a high rank constraint once, candidate 1, which violates a lower rank constraint twice. Which is the winner? The answer is candidate 1, choice A here. Why is that? Well, once the first constraint is ranked above the second constraint, then it becomes irrelevant how many times this lower rank constraint is violated. If you follow the algorithm, we start with the highest rank constraint first. If we eliminate any candidates, and we do, we eliminate candidate 2 here, then we check to see if there's more than one candidate left. There isn't. We already have a winner or an output, candidate 1. Doesn't matter what happens with this lower rank constraint. Doesn't matter if candidate 1 violates this constraint twice. Doesn't matter if it violates it 5 times. Doesn't matter if it violates it 100 times. This is the nature of OT. It's one of the hypotheses that the framework is built on, that there's a strict prioritization or a hierarchy of constraints in the ranking, and higher rank constraints are categorically sort of dominate the lower ranked ones. And it doesn't matter how many times you violate a lower ranked constraint, it will never be enough to overcome a higher ranked constraint. There are versions of phonology that are sort of like slightly different quantitative versions of OT where this does matter. But in strict classical optimality theory, which is what we're doing in this class, this is the situation. Once a higher rank constraint rules out some candidate or favors some candidate as the output, no number of violations of a lower rank constraint will ever be enough to overcome that. That's one of the hypotheses of the theory. Okay, here's some slightly more complicated ones. 3 candidates here. Which one wins? And here it's going to be candidate 3. And again, if you end up with a tableau where there's some candidate that doesn't violate a single constraint, it might mean that you've done something wrong with the analysis. There might be a relevant constraint that you've left out or something like that, although not always, but this should make you slightly suspicious. Why does candidate 3 win? Well, because for the high rank constraint, we eliminate candidate 2 because it violates this once where the minimum is 0. And same thing for constraint 2. Now we're down to only considering A and C. B is already out. The minimum number of violations here is 0. Candidate 1 violates it once, therefore this is out as well. And now candidate 3 is the only one remaining. Last one here. Which candidate wins this setup? This is another somewhat tricky one. And here it's going to be candidate 1 that wins. Why is that? Well, the highest rank constraint has a minimal number of violations of 0 for both these candidates. Candidate 3 is eliminated because it violates it more than the minimum number of times. We're left with candidates A and B. On the next constraint down, what's the minimal number of violations here? Well, 1. If candidate 3 had survived, then we would say 0. But because candidate 3 is already out at this step, we're only considering these 2. The minimal number of violations is 1. And is there a candidate that violates this more than the minimal number of times? Yes. Candidate 2 violates this constraint twice. So we eliminate candidate 2. The output is candidate 1.